Understand curvature, what we want to do is to think about how a curve changes and turns at a particular point in space. So for example, if I draw a trajectory that has a very tight curvature in it, and we'll just let the parameter arc length as a parameter start here, and change that, or compare that rather, to a trajectory that doesn't have a lot of curvature, is not a very tight curve, and then draw and think about what happens as the tangent changes. So if I draw the tangent vector at this point in space, is that sometime s, and then I do that sometime later, some small time later, but remember we're talking generally differentials here, so that then I take those two vectors off and try to draw parallel vectors that are out in space, and that you can see I end up with a very large value of the curvature. So this is a large curvature, the number that results from the resulting magnitude of the vector. Whoops, too many s's, sorry. S plus delta s minus t of s, the vector, the tangent vector in that direction. So now let me compare that to the idea of creating the tangent vector on this same s and delta s that I did on the steep bend on the left-hand side, and now transfer these two vectors roughly parallel so that I can say that if I take that same difference and compare it to the first one, this same difference here, I have a small curvature. So, so if I just take the magnitude of that value, right, and of course you take it in a limit as delta s goes to 0 and so forth. And so what we're going to do is talk about the rate at which the tangent vector changes. Okay, and that vector, tangent vector t, changes. So we can see in this particular case with a steep curve is that I end up with a large curvature, and that here I end up with a small curvature. And what we're going to do is call that value kappa, which is a Greek letter, kappa, that is then the magnitude at which the tangent vector changes. Okay, so that's our definition. What we want to notice and realize about this definition is that, number one, it's referring to arc length. S is the arc length. So that we need a description of the curve with arc length, which isn't always easy to get to. And then we're just saying that this is going to be our change in the tangent vector with arc length. So that we can say that, okay, so now we have a large curvature, and that's a very bended curve, and we have a small curvature and a very kind of smooth curve. Right? So we can talk about how this works now. If we look at the idea that what we want to do is then create the idea about what's happening, right? So we want to talk about the change in the tangent vector with time. And if I just do my chain rule, I can say that that's the change in the tangent vector due to arc length times the change in arc length with time, right? Because t is a function of arc length is a function of the parameter, and so that we can then make that rule using the chain rule. So we already know that the change in arc length with time is the magnitude of the velocity, okay, or the speed. So that once we put those two pieces together, this value of kappa here at the end, let me change this to, we'll just do it in black, is that the value of kappa is then magnitude of the tangent, change in the tangent vector with arc length. But I can write that as the change in the tangent with value and the change in the arc length with the value, just by using the differential dt as a common denominator in the numerator and denominator. So now the denominator here, we already know, is the speed. So then I can write that as, now let me just copy this over here, kappa of s is 1 over that speed times the change in the tangent vector with time. Mm-hmm. So a way to write this as our final challenge, or not challenge, but our final statement would be to continue. Let me just erase this a little bit here, and then we'll just extend this box and say that that's going to be equal to the magnitude of the change in the tangent vector divided by, that's what our numerator was here, right, d dt dt, and the denominator is going to be that speed. Right? So there is kind of a capsule version of how we talk about the curvature.